Good afternoon, everybody. Today I will talk about ML descent, an optimization algorithm for full waveform inversion using machine learning. My name is Bingbing Sun, and my co-author is Tariq Khalifa, both of us coming from King Abdullah University of Science and Technology. Usually, we use a handcrafted algorithm to solve optimization problems. Such human-designed algorithm is general and not specific to certain inverse or optimization problem. For example, in the figures, I show that a general human-designed algorithm, the great descent, will oscillate around a valley, and we propose to learn an optimizer which is specific to your problem and the data, and thus the learned algorithm may have been seeing this zigzag oscillation behavior before and find a better and faster converging solution for the optimization. If we want the machine learn our optimization algorithm, we need at first to gain insight of the current human-designed optimization algorithm first. Here I summarize and present a generalized form for all the optimization algorithms, such as nonlinear-conjugate gradient descent, or LBFGS. For descent direction-based optimization algorithm, the updating direction delta x of current steps will depend on the gradient and updating direction at the previous step. Different optimization differs the way how to use such history information. Here is an example, the nonlinear-conjugate gradient method. The updating direction at the current step is a linear combination of the current gradient and the updating direction at the previous step. Thus, the question is how to introduce the history dependency features of the optimization algorithms using a neural network. How to track of the history information when we try to learn and train our optimization algorithms using machine. The RNN is the ideal neural network for this purpose. Here is a figure showing an RNN with an input vector xt and output vector yt. A loop allows the information to be passed from one step of the neural network to the next. There are variations of RNN, such as a long short-term memory, LSTM, and the gated recurrent unit, GRU. In this paper, we use LSTM for design a network to learn the optimization algorithm. In each time step, the input is the gradient G, and output would be the updating direction. For a typical 3D full waveform application, the number of model parameters can be on the scale of millions. Optimization for this scale with a fully connected RNN is not easier because it would require huge hidden states and an enormous number of parameters RNN. Thus, we use a modified RNN which operates coordinate-wise on the parameters of the objective function. We can run full waveform inversion on randomly generated velocity models to train the RNN. However, a typical time domain FWI requires solving a partial differential equation to model the data and to construct the gradient, which tends to be computationally expensive. However, any nonlinear inversion problem can be approximated locally by a linear problem. Thus, we design many linear problems for efficient training. One simple option is to use a random generalized quadratic functions. Here the matrix W as well as the vector B is randomly chosen. We use a DAM and we train for 100 approaches, and each approach will train on 2,000 such randomly generated quadratic functions. The decreasing of the loss indicates the success of training our algorithm. After training, we compared with our machine learning algorithm with other optimization algorithms, such as statistical gradient descent, (DAM). The results show that our machine learned ML descent gives the best performance in the abstract of the fast convergence speed and the final smallness residue value. So after finishing training of the corrective functions, we now can apply our learned optimization algorithm to the Mammochi-2 model. Mammochi-2 model is an elastic model, and thus our testing is free of inverse crime. That means we perform acoustic FWI with data obtained from elastic modeling. In the inversion, we use 5 Hz recall wavelet with 50 shoots and 425 receivers, evenly spaced on the space. We perform a 4-band inversion. That means we do not perform frequency continuation from low frequency to high frequency. Here is the initial model for the acoustic FWI. It is burned by a Gaussian spoof of the true VP model. Here is the result of the ML descent result of the acoustic FWI of the Mammochi-2 model. We can see the ML descent with the Convex model with high resolution. Also, notice that we perform an acoustic FWI with elastic dataset. This demonstrates that our method is capable of being used in realistic FWI applications. Here we show the results by other optimization algorithms. We can see that ML descent is the best. MS Pro is good but slightly low resolution. The advantage of the ML descent is further demonstrated with the misfit over iterations. ML descent finishes the inversion with the lowest residue. We have our conclusion here. We generalize optimization algorithm and use IN to accommodate the history information to learn a model updating schemes for FWI. The work is mainly following the method proposed by DeepMind, and we also publish our work in GeoPhysics. If you are interested in our work, you can refer to our paper for more details. And thank you.